Welcome to the first lecture of module 4. In this module, we will discuss the reactor design. Mostly we will consider ideal reactor design in this module. Before going to this lecture, let us have brief recap on our previous lectures which we had in our module 3. In module 3, basically we have considered analysis of the batch reactor kinetic data. So, several cases for the analysis of the batch reactor kinetic data we have considered. First, we have considered the constant volume system and we have considered two method of analysis. One is integral method of analysis and another one is differential method of analysis. In integral method of analysis, we have assumed a kinetic rate laws and then we tested the integral form of the rate equations and we have seen whether that is fitted with the data obtained from the batch reactor data. In the differential form of analysis, we have seen that we have taken the rate equations and we have directly fitted the data which we have obtained from the batch reactor. And we have analyzed each method's merits and demerits, like when the data is scattered, we cannot use the differential method of analysis. Instead, we can use the integral method of analysis. The other cases which we have considered is the variable volume systems, and variable volume systems generally occur in case of the gas phase reactions, in particular where the moles of the reactants and products varies before and after the reaction. And we have considered differential method of analysis as well as the integral method of analysis. Now, in this lecture we will consider introduction to the reactor design and we will consider ideal batch reactor design in this lecture. The broad outline of this lecture would be introduction, then decoupling mass and energy balances, general mole balance equation, and then we will consider ideal batch reactor design. For batch reactor, we will see the space time and space velocity, how they are related each other. So, introduction to the reactor design. The basis for designing any reactor is the set of fundamental balance equation. When we set up fundamental balance equations, what are these equations represents? These equations represents the mathematical statement of physical laws. So, when we say mathematical statement of physical laws, what does it mean? The physical laws means it requires that the conservation of mass or conservation of momentum or conservation of energy. In addition, we can have conservation of quantities of particular chemical species which we wanted to follow for a particular reaction. What is the objectives then? Our prime objectives over here is to know what size and type of reactor and method of operations are the best for a given job. So, we need to find out the reactor size and what type of reactor we need and the method of operation to obtain the best result for a given job. So, with this basis we can start the ideal reactor design, but before going to this, let us have our great scientist Albert Einstein taught us that mass and energy of a system are proportional. That means, if a system loses energy, its mass decreases. If it gains energy, its mass increases. So, the relationship between the mass and energy is given is equal to E is equal to mc square, which is well known equations. Now, from this relation we can see that mass and energy are equivalent and they are simply different forms of the same entity. So, let us consider the combustion of methane. This reactions of combustion of methane is a very high exothermic chemical reaction. As we can see, methane reacts with oxygen, forms carbon dioxide and water, H2O, water vapor. So, this reaction when occurs, 1 mole of, say, if we consider one from the stoichiometry, if we look into 1 mole of methane is completely burned with 2 mole of oxygen. If that is happened for complete combustion of methane in presence of oxygen, the stoichiometric amount of oxygen will be used to burn 1 mole of methane. So, it will take 16 gram plus 64 gram. So, total 80 gram in total when it will react, and it will form carbon dioxide and water vapor. So, the reaction scheme is given over here, say methane and oxygen at 25 degree centigrade and 1 atmosphere pressure, it reacts in a reactor, then this is exothermic reactions. So, we need to take out the heat to keep the temperature same as it was before the reaction. So, to cool down to 25 degree centigrade and 1 atmosphere pressure. So, we are getting the product carbon dioxide and water at 25 degree centigrade and 1 atmosphere. So, the amount of heat because of this highly exothermic reactions releases Q is equal to 802 kilojoule of energy. So, if we consider this energy and if we apply this E is equal to mc square formula, we can see that the corresponding decrease in the mass is about 9 nanogram, which is 9 into 10 to the power minus 9 gram. So, the mass change, suppose if we start with 80 gram of total reactants, it will give 79.99999991 gram product. So, the decrease of mass from 80 gram to 9 into 10 to the power minus 9 gram. So, 9 nanograms. So, which is very small. Now, let us see that decoupling of mass and energy balances. What does it mean? As we can see, even if for very highly exothermic chemical reactions, the mass changes in the chemical reactions are extremely small and usually much too small to even detect. So, as we can see in the earlier examples of methane combustion, the mass change is 10 to the power minus 9 gram, 9 into 10 to the power minus 9 gram, which is 9 nanogram. It is very difficult to use any equipment to detect that small change in the mass. So, therefore, we can decouple the mass and energy balances and make two separate assumptions. So, we can make two separate assumptions. What are they? Mass is conserved in all chemical processes and energy is conserved in all chemical processes. With these assumptions that for highly exothermic chemical reactions in general, the change of mass due to the chemical reactions is negligible or insignificant, or it is difficult to detect. So, in that case we can assume these two separate assumptions, that is, mass is conserved in all chemical processes and energy is conserved in all chemical processes. However, if we look into the nuclear reactions, for nuclear processes this is not valid, this statement is not valid. That means the energy changes are huge, so that the mass changes are significant. So, in that case for nuclear reactions we cannot decouple mass and energy balances. Now, let us consider general mole balance. We need to select a control volume, and that control volume could be an entire reactor volume. So, we can take, if it is gas phase reactions, we can consider entire reactor is the control volume, or we can consider a catalyst palette could be one reactor volume or control volume, could be an infinitesimally small element of volume within the reactor. So, we can consider very small element inside the reactor as the control volume. So, let us consider this is our system volume or control volume, whose volume is V, and the feed which is entering, the moles which is entering into this control volume is Fj naught, and the mole which is going out is Fj, and Gj is the amount which is generated due to the chemical reactions in this control volume. Now, let us do the mole balance. So, if we do the mole balance for a species J at any instant in time t, we can write rate of flow of J into the system, that is Fj naught, plus rate of generation of any J component J by chemical reactions within the system, minus rate of flow out of J of the system, which would be equal to rate of accumulation of J within the system. So, rate of flow of J into the system, which is in moles per time, this is also the generation Gj, which is also in moles per time, and the flow which is coming out from the reactor is also moles per time, and the accumulation within the system should be moles per time as well. So, the unit should be same. So, in simpler form, this we can write in plus generation minus out would be equal to accumulation. So, these are the simple mole balance equation for any species J at any instant t. Now, the overall mole balance equation is in plus generation minus out is equal to accumulation. So, in this case the in is Fj naught plus generation is Gj minus out, moles of the component out is Fj, which is equal to the accumulation if Nj is the number of moles of species J in the system at any time, t, then the accumulation term we can write dnj dt. Now, if this system is specially uniform, that means, so if it is specially uniform system, then we can write Gj would be equal to Rj, rate of reactions of component J into the volume of the system. So, for specially uniform system, Gj would be equal to Rj into V. Now, if it is not specially uniform, then what will happen? The formation of species J for the reaction varies with the position. In the system volume. Say, if we consider Rj1 is at location 1 with small volume delta V1 and Rj2 at location 2 with small volume delta V2. So, like this is a small volume which is delta V1 at location 1 with no rate is Rj1. And if we consider another volume which is at location 2 is delta V2 and Rj2. So, this is in and this is out. So, in this we have considered two control volume at very small volume at two different location. So, we can write delta G J1 would be equal to Rj1 delta V1 and delta G J2 would be equal to Rj2 delta V2, because they are not specially uniform. So, two different locations delta G J1 and delta G J2 would be different. Now, if we consider m number of subvolumes, say consider m numbers of subvolumes. So, if we consider m number of subvolumes, we can write Gj would be equal to summation over I is equal to 1 to m delta Gj I, which is equal to summation over I is equal to 1 to m r I r j I delta V I. So, if we take the limit, taking limit m tends to infinity and delta V tends to 0, very small volume. If we take these limits, then we obtain Gj is equal to summation over I is equal to 1 to m limit delta V tends to 0 and m tends to infinity, r j I delta V I would be equal to integral r j dV. So, integral V r j dV. So, then the balance equations which we have done earlier, that is f j naught minus plus g j minus f j is equal to d n j dt. Now, if we substitute g j over here, we would obtain f j naught minus f j plus integral over v r j dv would be equal to d n j dt. So, this is the general mole valence equation. We will use this general mole valence equation for different ideal reactor design. Let us consider ideal batch reactor design. So, if we consider ideal batch reactor, which is fitted with a stirrer, and this is filled. So, initially this is charged with a feed and then it is closed. So, this is not a flow system. So, in this case Fj naught would be equal to Fj, which is equal to 0. So, now if we take the general mole balance equation, that is Fj naught minus Fj plus integral V Rj dV is equal to dNj dt. So, in this case, if we apply this for the batch reactor, then this would be 0, this is 0. So, we would get from here dNj dt is equal to integral V Rj dV. So, this is the mole balance equation for the batch reactor. Now, if we consider reactant A, for reactant A we can write the moles Na would be equal to Na naught minus Na naught Xa. So, while writing this, we have considered a general reactions A to B. So, the conversion is Xa. So, this would be Na naught into 1 minus Xa. So, we can write dNA from here, dNA dt, if we differentiate, this would be equal to minus Na naught dxa dt, and we know minus Ra is equal to minus 1 by V dNA dt. Now, if we substitute this dNA dt from here, so we would obtain Na naught by V dxa dt. So, now if we consider the general balance equation for the batch reactor, that is minus dNj dt is equal to integral V minus Rj dV. So, if we substitute this one with for component A, we can write Na naught dxa dt is equal to integral V minus Rj dV. Now, for a perfectly mixed reaction mixture, for perfectly mixed reaction mixture, means this is homogeneously mixed. There is no variation of Rj with position. There is no variation of minus Rj with position. So, then we can write from here, therefore, we can write Na naught dxa dt is equal to minus Rj into V. Now, if we rearrange this equation and then if we integrate, so rearrangement and integration if we do, we would obtain Na naught dxa dt is equal to minus Rj V. So, we can write from here dt is equal to Na naught dxa by minus Rj V. For component A, it is Ra, now if we integrate this, so when t is equal to 0, xa is equal to 0, dxa by minus Ra into V, when t is equal to t, xa is equal to xa. So, this is we will get t is equal to Na naught integral 0 to xa dxa by minus Ra into V. So, this is the general equation showing time required to achieve a conversion X A to achieve a conversion X A for both cases. Isothermal and non-isothermal. And another feature for this, we can see the volume of reacting fluid V, the volume of reacting fluid and the reaction rate remain under the integral sign. So, this means that in general the rate of reactions and the volume, they change during the course of the reaction. Now, if we just plot these general equations for concentration versus or conversion versus time, it will show a curve like this. Now, consider two limiting cases. In one case, it is constant density system. If it is constant density system, so our general equations is T is equal to Na naught integral 0 to x a dx a by minus R a into V. Case 1, constant density system. That means the volume is constant. So, this we can take out from here and we can write T is equal to Na naught by V integral 0 to x a dx a by minus R a, or this would be equal to, since V is equal to V naught constant volume. So, this would be equal to C a naught integral 0 to x a dx a by minus R a. We can also write it is minus integral C a naught to C a dC a by minus R a. So, for constant density system, so your epsilon A is equal to 0. Now, if density changes, case 2, density changes, then this T would be equal to Na naught integral 0 to x a dx a divided by minus R a into the volume is linearly related with the conversion, as we have discussed before. So, we can write V in place of V, we can write V naught into 1 plus epsilon A x a. So, here we can write Na naught by V naught. So, it will be C a naught integral 0 to x a dx a divided by minus R a into 1 plus epsilon A x a. So, this is applicable for both isothermal and non-isothermal systems, and this is for any epsilon A, any change in volume. But in case of the non-isothermal system, the variation of rate with temperature, that is the function of temperature of R a and the variation of temperature with the conversion, that is X A is function of temperature, should be known to use this relation for non-isothermal system. So, this is the two special cases for the batch reactor. So, now we will consider space time and space velocity. For the batch reactor, we know the reaction time T is the natural performance measure of batch reactor. Space time and space velocity, these two terms these are the proper performance measure of the flow reactor. Now, how to define space time? It is symbolized with tau instead of t, it is symbolized with tau, and the space velocity is represented with s. So, which is 1 by a, tau would be equal to 1 by s, and it is defined as time required to process one reactor volume of feed measured at specified condition. So, this is unit of time. As it is said, the time required to process one reactor volume of feed measured at specified conditions. So, condition has to be specified and the time required to process one reactor volume of feed is the space time. Now, for space velocity, it can be defined as the similar way, s would be equal to 1 by tau, which is the number of reactor volume that can be processed in unit time. So, it is defined as number of reactor volume of feed at specified conditions, which can be treated at unit time. So, the unit of this is time inverse. So, as we can see, this the reactor volumes of the feed should be mentioned at a particular conditions, that condition has to be specified. So, that we can define the space time and space velocity are based on a particular specified conditions. Now, what do you mean by space velocity of 5 hours inverse? This means that five reactor volumes of feet at specified conditions are being fed into or treated in the reactor per hour. So, 5 reactor volumes of feed at specified conditions are being fed into the reactor or treated in the reactor per hour. So, that indicates the space velocity of 5 hour inverse. Now, if we say what do you mean by space time of 2 minute? The space time of 2 minutes means that every 2 minute one reactor volume of the feed at specified conditions is being treated by the reactor. So, this means at every 2 minutes one reactor volume of the feed at specified conditions is being treated by the reactor, which is significance of space time of 2 minute. Now, we may arbitrarily select the temperature, pressure and state. So, for a particular feed we may arbitrarily select the temperature, the pressure and the state, say gas, liquid or solid. So, if the space time or space velocity they are on the basis of the entering conditions, that means if t, tau and s are based on entering conditions, to the reactor, then we can write tau is equal to 1 by S is equal to Ca naught V divided by Fa naught, that is moles of A entering, moles of A entering for volume of feed multiplied by the volume of reactor divided by moles of A entering per time. So, this would be equal to volume of reactor divided by the volume of feed. So, this is V by V naught per time. So, volume of the reactor divided by the volumetric flow rate. So, V by V naught. Now, it may be more convenient in certain cases to define the space time and space velocity at some standard conditions, particularly when the reactor operates at various temperature. So, more convenient to use to measure the volumetric flow rate, that is V naught, at some standard state. Especially when the reactor operates at numbers of temperature. For example, if we take some gaseous reactant which are fed to the reactor and which is at high temperature, and then the same thing is liquid at the standard conditions. So, in that case we should take care of the defining the state of the conditions. Now, if we write the actual conditions which is unprimed and standard conditions with primed, actual condition unprimed, standard condition primed, we can write tau dash is equal to 1 by S dash would be equal to Ca naught dash into V divided by Fa naught, which is equal to tau Ca naught dash by Ca naught, which is equal to 1 by S Ca naught dash by Ca naught. So, this way we can relate between the actual conditions and the standard conditions, space time and space velocity. So, thank you very much for attending this lecture, and we will continue the reactor design for other idealized reactor in the next lecture.